Good afternoon, everybody. I'm Giorgio Veronesi. I'm the president of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for almost 9 years, and currently I'm in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects around the world with the several assignments overseas. I'm very happy to be involved in the introduction of this webinar on the very current theme, electrifying the chemical industry, and I'm really looking forward to participating to it. Let me say something about this Spotlight Talk series. This is now our 5th year of this initiative, which started in 2020 to keep together the chemical engineering community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight Talks into a regular feature of EFCE program. And so we have now 2 series in even years, spring and autumn, and 1 series spring in odd years when we are holding the European Conference of Chemical Engineering in autumn. Let me take this opportunity to remind you that next year in September 25, we will hold the European Conference in Lisbon, an event not to be missed, September 25. This fall, we have 13 of our working parties and sections: sustainability, mixing, electrochemical engineering today, high pressure technology, food, loss prevention and safety promotion in the process industries, agglomeration, multi-phase fluid flow, static electricity in industry, education, polymer reaction and engineering, thermodynamics and transport properties, and finally early career chemical engineers, delivering over 2 weeks a short session of 3 or 4 talks focused on specific topics by leading industry and academy experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interest. If you are interested or if you want to know more, you can check on our website the complete program. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 of them in Europe. And EFCE working party and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. I'm very particularly happy that in this series of Spotlight Talk, we'll have the first contribution of the newly re-established section on sustainability. Actually, it was held yesterday with one separate Spotlight Talk and another organized with a working party on education. As you know, sustainability starts with education. Okay, before concluding, I would like to thank all the people who work hard inside the working parties section and EFCE in general for this initiative to happen and to be successful. And in particular, I would like to express my heartfelt thanks to EFCE Martin Pou in Toulouse of the Scientific Secretariat, who did most of the work from the conceptual phase to setting up and all practical activities. I thank you all for attending, and particularly the speakers, and I wish all the speakers and the attendees a fruitful and successful webinar. And then I'm giving the floor to Professor Karel Bouzek from Prague, Chair of the Working Party on Electrochemical Engineering, to introduce the works. Karel, please go ahead.
Thank you, Giorgio, for introduction. So most of the words was already said, but anyway, as it was said, my name is Karel Bouzek. I'm coming from UCT Prague, and it's my pleasure to welcome you at this first Spotlight Talk organized by our Working Party on Electrochemical Engineering. As it was said, the topic is electrifying chemical industry. which is very hot topic considering our trial to decarbonize our societies and to save CO2 reduction emissions. And it's clear that electrochemistry plays an important role in this process as it allows to convert the renewable electrical energy to the energy of chemical bond, so directly related to our chemical industry and to many other sectors. But it's not only electrochemistry, so the electrochemical discoveries or electrochemist discoveries needs to be transformed to the applications, to the technologies, scale up, optimized, which is the work of the engineers in general, and in this particular case, of the electrochemical engineers. So I'm glad that we have on this way opportunity to present to you the achievements and new trends in this field. And not to be very long on my time, I would like to thank also very much to Michele Tedesco for TNO who take over the responsibility for organizing this spotlight talk. Of course, to great speakers he has attracted to this presentation, that they offer their time and their knowledge to be shared with us, and to all the attendees who are interested in this field and join us for this webinar. And by this, I would like to wish to all of us fruitful and interesting event now. Thank you very much.
Thank you very much, Karel. Welcome everyone also from my side. My name is Michele Tedesco. I work as a scientist on electrochemical engineering at TNO in the Netherlands. It's my pleasure to be here as a host today. Enough has been said on the introduction. So the only thing I want to add is that if you have questions during the presentation after, you can put them in the chat and I will read them out loud. Hopefully there will be enough time to answer all the questions. Otherwise, the speaker will be asked to reply directly in the chat for the questions that are not answered plenary. And with that, I would like to already start with the first speaker, a colleague at TNO, so is Dr. Arend Groot. Arend is a senior consultant on green hydrogen at TNO, where he leads a group of more than 50 scientists and researchers that collaborates with industrial partners to develop a next generation water electrolyzers. So Arend has published on diverse topics related to hydrogen, for example, on the first European hydrogen implementation scenario studies, on the electrification potential for the Dutch industries, and on infrastructure and technology assessment on a range of hydrogen production technologies. So he's definitely the best speaker I can think of today to kickstart this first part of the webinars focusing about green hydrogen. So Arend, please, the floor is yours.
Thank you very much, Michele and Giorgio and Karel for the introduction and the opportunity to present here. I will share my presentation. No. Are you seeing my presentation?
Not yet in full screen mode.
Okay, no, but it should work like this. Okay, very good.
No, you need to swap now the display settings. We see the back mode.
Sorry.
Top left. Top in the top. Yeah, the second button there, that one.
Yeah. Yeah, okay. My apologies.
Yeah, go ahead.
Very good. Okay. Yeah, I will talk about next generation electrolyzers and with the subtitle, why future electrolyzers will still be much better. So the baseline of the talk is why there is still very much improvement potential for electrolyzers. And let me first show a figure which shows that this is also quite necessary. I think a lot of people are aware that there have been recently quite a lot of delays announced of investment decisions. And one of the reasons for that is that the cost of electrolyzer systems is still very high. And Paola, after me, will discuss what the consequences are for, let's say, the business case. What I want to focus on is what are the possibilities to reduce that. But to show let's say, the state of affairs, our colleagues at TNO in our Amsterdam department did prepared an evaluation of actual cost of projects which are being executed and planned in the Netherlands. They got a lot of confidential data, and they put together, based on those data, what the cost of hydrogen would be. And based on, and of course, these are piloting systems and demonstration systems, so it's not the real stuff yet. But what it shows is that the cost of hydrogen from the current piloting is well, almost an order of magnitude higher than we're targeting. By the way, this is a public report which you can download. I put the name of the report there. I talk about the potential to reduce or increase the performance, reduce the cost of electrolyzers. Specifically, I will discuss PEM electrolyzers, but in general, the story that I tell is representative also for the other technologies. But for the sake of simplicity, I will focus on a single technology. I will discuss what is necessary to bring down the cost of the electrolyzers, but also what are the challenges in getting innovations to the market. So getting them from the lab to real implementations. I'll discuss some of the key innovations which will help improve the PEM electrolyzer. And I'll give one example of an innovation to show how important the system engineering approach is in assessing how to implement the innovations. By the way, I work in Petten, in the part of TNO, and TNO is the Dutch Applied Research Organization with indeed almost 50 colleagues on different electrolysis technologies. Now, one of the questions is that we often get is, but electrolysis is a mature technology. There are electrolyzers in the market. And to illustrate that, before I go into the cost reduction, let me show what we call the concept of electrolyzer generations. Because yes, there are electrolyzers on the market at this moment, but as is the narrative of this talk, there is still a lot of improvement possible and necessary, as shown in the previous slide on the cost. And therefore we distinguish different generations, where we call generation 1, let's say, the systems which are currently commercial. We consider a second generation a very much improved generation of electrolyzers, which uses improved and advanced components, which uses all kinds of new technology, but still uses the, let's say, existing architecture of the electrolyzer. And we consider a third generation, which has really a radical redesign of the electrolyzer, the components, the nanostructures, etc. So that gives you a bit of a flavor. Yes, it's a high TRL technology, but if we're talking about the next generations, there's still quite a lot to be gained. Looking specifically at the cost, and there's a need to go to lower cost, but there's also quite some possibilities. Two, let's say, technology factors are producing electrolyzers at a much higher volume and standardizing components. That will certainly lead to cost reduction. That's also one of the steps in the first and second generation, and there's all kind of technology breakthroughs which we can use to reduce the cost. I also explicitly put risk reduction over the supply chain, and I will use the next sheets to illustrate how risk is adding to the cost of green hydrogen at this moment. If you now look at the manufacture of components, there's very limited manufacturing at scale, because taking the risk to invest in that scale at this moment is difficult. If we look at the component level, what you see is, for example, that in PEM electrolyzers, quite high loadings of critical raw materials are used, just to be sure that they can supply the lifetime. If you look at, again, the electrolyzer stack manufacturer, he will buy an electrode which may not be the cheapest, but which has a good track record. And there's limited suppliers, and they have invested a lot in developing those electrodes. So those electrodes will also include a risk factor. Same happens on the level of an electrolyzer stack. What you see is, for example, that ThyssenKrupp is doing quite well, because they have a stack which has been validated extensively in the chloralkali technology. It's not the cheapest design, but it has been validated. Well, to cut that short, on every level of this supply chain, from the manufacturing technology to the operation of the system, there are risks, and all those risks accumulatively lead to very high cost at the moment. They are an important explanation of why the capex costs are so high at this moment. The positive side is that there are in every level enough innovations which can improve the performance and reduce the cost. From roll-to-roll manufacturing, innovative designs of electrodes, innovative designs of electrolyzers. We can reduce the plant complexity if we have more information about the safety of systems. So on every level, there are a lot of innovations which can reduce the cost and improve the performance. But at this moment, the challenge is to bring those innovations rapidly to the market. And again, that is related to all the risks that there are. And that's why it's important to generate data, to develop standards, to develop benchmarks, so that we can accelerate the implementation of innovations in the industry. Let me talk about some of the innovations. And for PEM, I made a list. It's not an exhaustive list, but some examples of innovations which could improve the technology. The improved technology is, for example, a better performance or better efficiency, which can be achieved by making the membranes thinner. It can be achieved by improving the hydrodynamic design of the electrode, or the porous transfer layer, as it's called in the PEM technology. It can be improved by having membranes with better properties, or better catalyst. So there's a lot of things that can improve the performance. It's not only performance in the sense of efficiency, which is key, but we're also trying to improve the circularity of the electrolyzer. And in PEM technology, it's especially the use of iridium, which is critical, which is a critical raw material, which is not very widely available. So we need to optimize the technology to reduce our use of iridium. But also a very an issue which plays very much today is the use of PFAS, and the membrane that we currently use in the PEM electrolyzer is a PFAS-based membrane. So we're looking for PFAS-free membranes. There's issues which can improve the scale up, like improving the flow and current distribution over the cell and between the cells in a stack, or reducing the sensitivity to the compression force, which makes the components more forgiving for the stack design, or issues which are simply related to cost. Currently, in the commercial electrolyzers, there's a lot of noble metal coatings used just to be sure that we can achieve the lifetime. Replacing those by non-noble metals or removing the coating as such will reduce the cost. So there's a lot of different options for innovation. Again, it's not an exhaustive list, but what is also important is that there's a very complex interplay between the efficiency, the durability, the cost, and the circularity. We can, for example, reduce quite easily the loading of the catalyst by an order of magnitude, but then we run into issues with the durability. And the same is if we replace our PFAS membranes with PFAS-free, again, durability or the efficiency at which we can operate will suffer. So it's a complex interaction. How does that work out in the future performance of the electrolyzer? What we do to predict the performance of the future electrolyzer, or the future performance of the electrolyzer, is that we look at the state of the art. And then here at TNO, we use our in-house reference cell for that. And then we model the cell based on the data we get from the lab. And then we use the innovations, as just discussed, to see if we implement those innovations into our electrolyzer, what does that mean for the performance that we can expect in 2030? As an example of a time frame that we look at. One of the innovations which can give a much better performance is making the membrane thinner. Currently, the membrane is about 100 to 180 microns thick. That's much thicker than is used in fuel cells, with a reason, because the pressure differences are much larger. But we would like to go to much thinner membranes because an important part of the losses is in the ohmic resistance of that membrane. Again, I'm giving a single example here of an innovation, and you need to look at the whole balance of durability, circularity, and efficiency. So it's not all about efficiency. Actually, durability is one of the key issues that we need to address. Then let me take this example, this thin membrane, to look at how we assess the impact of such an innovation, the thinner membrane, in a system engineering approach. One of the impacts of having a thinner membrane is that you have less losses over your membrane, so your efficiency will be better. But there's a second impact, which is important, and that is if you make your membrane thinner, you will get more leakage through the membrane. There is always some leakage of hydrogen to the oxygen side and oxygen to the hydrogen side, which is called the gas crossover. And as we make the membrane thinner, the efficiency increases, but the gas crossover will increase. And that is a safety issue. In the case of the PEM, we can handle that quite well by using a recombination catalyst. So hydrogen, which leaks to the oxygen, reacts with the oxygen to remove the danger. But it's also an efficiency issue because it leads to a lower hydrogen yield. On one hand, because the hydrogen leaks to the oxygen side and is lost. But on the other hand, if we have oxygen leaking to the hydrogen side, we need to use a recombination catalyst downstream. And again, that leads to loss of hydrogen as well. What the figure on the left shows is the gas crossover as a function of the load. And it shows that there's a safety limit. And as we make the membrane thinner, that line of the gas crossover will go higher, and we will have a lower efficiency and run into a safety limit earlier. Well, the impact of that of those two effects is shown in the next sheet, where we look at the impact of the membrane thickness on efficiency. And what it shows is that there's quite a substantial impact of the membrane thickness. And the blue bar is the efficiency, but we also see that at lower loads, the extra loss that we have because of the gas leakage through the membrane starts to increase. So the optimum, if we look at low loads, is less than if we look at or is at a thicker membrane than at high load. Where it's clearly beneficial to go to a lower, thinner membrane. Now, this is for different situations. What we did was that we modeled the whole system over a lifetime. And we use the modeling an offshore use case because that's for the Netherlands an interesting one. So we looked at what is the impact of the membrane thickness if you look over the whole lifetime. And we looked at hydrogen production, which is the benefit, and the cost in terms of the stack replacement at the electricity consumed, which is related to the efficiency. We calculated over the 30-year lifetime for a whole for 30,000 years, 30 years. Sorry, and this is the impact on the efficiency. On the left, you see the total bar is the electricity generated by the wind farm. The green part is the hydrogen production, so that is also the efficiency of the system. And what we see is that if we go from 80 microns to 30 microns thick membranes, we have a substantial increase in our system efficiency, almost 10% higher efficiency if we go to this very thin membrane. But if we look at the levelized cost of hydrogen, we get a slightly different picture, because if we go to the thinner membrane, indeed our losses are lower, so our efficiency is better, but at the same time we have a more frequent stack replacement because of the thinner membrane. So if we look at the overall effect, we get a different picture for the optimum size of thickness of the membrane. And you could even say that the effect of going to this thinner membrane, taking into account the stack replacement, is very, very limited. Of course, this depends on the durability of the stack, which we will improve. It depends on a lot of different things and the cost of the stack. But what this shows is that it's important to have a good evaluation of the assessment of different innovations, looking at the system as a whole.
Arend, 2 minutes.
I see Michele appearing. I'm going to my conclusions. What is important is that we're trying to scale up the technology very rapidly. And that means that there's a lot of risks still in the whole supply chain. And if you accumulate all those risks in the supply chain, it leads to high costs. So we need to address those risks. One of the things is to make sure that we have more data, standards, and benchmarks, which enable us to bring innovations more rapidly to the market. And on the bright side, there are a lot of innovations which can help increase the durability, reduce the cost, improve the efficiency of the technology. And a key message, a system engineering approach is very important to assess innovations, as shown by the example of the membrane thickness optimization. Thank you very much.
Thank you very much, Arend. I see already there are 3 questions. So the first one is a multiple question. I will break it down from Julia Schobarten. So what alternatives are available to PFAS-based membranes? And are we referring to polymeric PFAS or also shorter chain PFAS, such as PFOA?
If you look at the PFAS-free membranes, the durability of those membranes is at this moment not at the level of the PFAS membrane. So there's quite a difference there. One of the things that is unclear in the regulations, because in principle, it's the use of membranes with PFAS in such a system as an electrolyzer does not necessarily lead to the PFAS emissions, which are dangerous. So in principle, maybe it would not be necessary to replace the PFAS as long as we can show that those emissions to the environment do not take place. So I don't think the solution is let's say going to other PFAS membranes. The solution would be either to go to PFAS free, or to go or to demonstrate very clearly that there's no emissions from the electrolyzer over the lifetime.
Thank you. And a follow-up was, have you encountered PFAS contamination in the process water or equipment?
The answer is no, but
Okay.
I'm not saying that we haven't, that's not the case. Actually, there's a lack of research on that topic. So that has been flagged indeed as necessary research.
Okay, thank you. See many questions popping up. The next one from Matthias Riechraff. Do you see a high risk that companies that build large manufacturing plants today will not be able to adapt their plant to new innovation at the cell and stack level due to the required redesigning of the manufacturing routes?
That's a good question. Indeed, there is a risk if you invest in technology which does not fit next generation. One of the big issues in the electrolyzer, in the PEP electrolyzer, is will we stick to the catalyst coated membrane, or will we go to electrodes which have the iridium coated on them? That's quite a fundamental difference in terms of manufacturing technology. So yes, I see that risk. And in addition, it's also the choice between the technologies, which is very difficult to assess at this moment. That's something that we're discussing a lot with industry. Issues, all technologies have different issues and disadvantages. So that's also a risk in the market. Yes.
So indeed, there is an extra risk on competitiveness. The next question is related again to PFAS. Are there alternative membranes available to replace Nafion yet? I think you already answered that question. The answer is no.
Yeah. No, not at the same level. There is work ongoing in that field, but yeah.
The next is about, can you comment on the global energy efficiency of the technology today, so compared to the thermodynamic one?
Yes. So I would say the efficiency is a choice. If I can put it that way. Currently, manufacturers focus on a very high current density because of the cost of the electrolyzer. Generating as much hydrogen as possible from a square meter is the wise thing to do. If you look at the current densities, which are usual, with let's say 2 to 3 amps per square centimeter, then you come with the current electrolyzers in the 60-70% range. It depends very much on how much the cost per square meter of an electrolyzer goes down, and of course there's a potential cost down for the stack itself. For the system, that's more complex, and it's a chemical plant in a certain sense. So we will not reduce the cost of the system by orders of magnitude. For the stack, that can be. So for a future electrolyzer, I would expect that the efficiency increase comes not only from, let's say, better components, for example, a thinner membrane, but also because we're able to mass manufacture and make the electrolyzer cheaper and work in a different operating window.
Thank you. The next one is about the cost impact of membrane use.
Yeah, that's a very difficult question to answer, because at this moment there's no mature market for the membranes. There are some companies who have invested quite heavily in developing the membranes, but the volumes which are sold are still very limited. So it's very difficult to make an assessment of the future cost of the membranes. In general, at this moment, it's one of the bigger cost factors.
Okay. So given the time, I will only read the last question, and then we'll ask you, Arend, to reply to another one in the chat. So last question for this Q&A is, what's the biggest hurdle in the reduction of levelized cost of hydrogen at the moment? Is it the catalyst or the membrane or the balance of plant? And have we reached a technological limit already in reducing the levelized cost of hydrogen?
Yeah, that's another difficult question, but I would say that at this moment, if you look at where there's a lot of additional cost, and I will also partially leave this question to Paola, but I think the balance of plant is a very important part of the cost today, and especially surrounding, let's say, the safety analysis and how what measures you need to take to have a safe operation of the plant.
So thanks. That's a clear answer for now. I would like to ask you, Arend, to also answer the last questions in the chat.
Yeah.
And thanks again. And now we move on to the next speaker. So Paola, could you please already share your screen?
Yes, of course.
So Paola, Dr. Paola Granados Mendoza, thank you for being here today. So she works as the technology manager for HyCC. So Paola has a PhD in electrochemical engineering from University of Eindhoven, and more than 10 years of experience in the field of electrolysis and process technology. And in her current role at HyCC, she is responsible for the technical development of two pilot scale installations, to large scales, for 500 megawatt water electrolysers in Amsterdam, and also a large project of water electrolysis in central Germany. So, Paola, thank you for being here today. The floor is yours.
Thank you very much, Michele, for the introduction. Just checking, do you see my screen, the presentation on full screen?
Yes.
Perfect. Okay. Well, thank you very much for this opportunity to give this presentation. Thank you also for the introduction. My presentation will be about the challenges of implementing water electrolysis at a larger scale. I'll first start with an overview of the landscape of the hydrogen economy, particularly focused for the industrial sector. And then I will give you what are the key aspects that off-takers in this sector consider. And then I will elaborate on the role of the electrochemical engineers on solving these challenges. Before I start my presentation, I want to give a very brief introduction about HyCC, the company where I work. So HyCC is the joint venture of between Novian and the Green Investment Group of Macquarie. And as a Dutch company, we develop water electrolysis plants in Netherlands and in Europe. And we built on our heritage of decades of electrolysis experience from our one of the joint venture partners, Novian, and we aim to own and operate the water electrolysis plants to deliver hydrogen to the key industrial sectors. And so my presentation is, as I said, is about the challenges of green hydrogen in the larger scale industrial uses. So when we look at in Europe, we have set very ambitious targets for green hydrogen. So we aim to produce domestically about 10 million tons and import a similar amount of renewable hydrogen by 2030. So this is a very ambitious target. This means that if we consider, let's say, a typical full load hours factors and efficiencies, producing these 10 million tons will correspond to about 90 to 100 gigawatt of electrolyzer capacity. So this is quite large, especially considering that in Europe, the largest water electrolysis plants that are operational are in the range of 20 megawatts only. So we see that there is an enormous upscaling effort that is required. Besides these ambitious targets, I think it's also good to have a reality check. When we look at, if I look back in the past, let's say 5-6 years before, it was more or less that every week there was an announcement of a new hydrogen project in Europe. So there was a surge of the expectations about green hydrogen and its uses. What we see also that in the recent times, the targets have been seen under a more critical lens and challenging them as maybe they're overly ambitious. Can we make it? Also, it has been taking a long time to define the regulations for this to be in place on European level and also on the different country level. And what we also see is that in the past year, I would say, or in the past months, a lot of investment decisions of these green hydrogen projects on large scale either have been delayed or put on hold or really completely stopped. So this makes me reflect. So these ups and downs of this development makes me reflect on this the so-called hype cycle. As you can see it in the figure, when developing a new technology, this typically follows a cycle that starts with an innovation trigger. Then it reaches a peak of inflated expectations. Then it goes through the through of disillusionment. And then after that, it slowly starts again what is called the slope of enlightenment and reaching the plateau of productivity. So I think this, what has been happening in the last years, at least it makes me reflect on this cycle. I think is a good challenge to say, well, where are we at the moment? I think that we are somewhere around here. I don't know if we have reached the bottom part, but I think it's also good to understand in this context what are the developments, or who are the off-takers for this larger scale, and then start looking at the challenges that we have there. So green hydrogen can be used to decarbonize the hard-to-abate industries. So, and you can think of, for example, ammonia production, steel, in refineries, methanol, etc. And these industries not only want and have their own targets, but they have also they need to also comply with European regulations with respect to targets. So, for example, the Renewable Energy Directive 3, the RED 3, sets very ambitious targets also for industrial use, where it requires more than 40% of what is called renewable fuels of non-biological origin. Among renewable hydrogen is one of them. To use by, for example, 2030. So for these industries to let's say to implement that, it's also a challenge. And why is a challenge? I think it was already mentioned or started introducing by the previous presentation by Arend. Green hydrogen is expensive. So we know that producing green hydrogen is more expensive than gray hydrogen. I think you often hear that the typical targets to be competitive are around €2 per kilogram of hydrogen or less. But in practice, the cost of hydrogen, of green hydrogen, is significantly higher. So public figures indicate that at best, and I think also Arend showed even higher figures, which probably are more reasonable, but at best, it's about €8 per kilogram. And when you look at, let's say, the levelized cost of hydrogen, so this you can see that the capex and the electricity, or for the production of hydrogen, play an important role in that. Other things, such as, for example, grid fees or taxes, which are country dependent, will also play a role, of course. So when I look from the off-taker perspective, and I like this quote from the CEO of Total Energies, that says, well, if I have to pay €8 per kilogram compared to €1 for a grey hydrogen, it needs to sink in. There's something it's not an easy decision to go for it. So looking also from the off-taker perspective, when we see, for example, where these hard-to-abate industries, what kind of processes they have. So these large-scale industrial processes are not always very flexible. So the off-takers typically require a baseload supply for hydrogen. And hydrogen, as you know, it is produced, green hydrogen is produced from renewable sources. So if it needs to be compliant with RED 2, and that fluctuates, electrolyzer technologies can be very flexible. However, the off-taker wants baseload. So, of course, ways to solve that is either by storing energy when it makes sense, or storing hydrogen locally, which is sometimes a challenge, or in, for example, underground storage facilities. And development of all the infrastructure around it, it also takes time, and is not an easy task. So when we zoom out again and looking at the challenges, let's say from the off-taker's perspective, I see that the electrochemical engineers play an important role. So what electrochemical engineering brings is basically bringing the knowledge from the fundamental research into the industrial application of those electrochemical processes. And for water electrolysis, typical challenges are or things that we need to consider are with respect to costs, performance, the flexible operations, maturity of the technology, and also safety. So I'm going to touch upon these topics, and I want to start first with the costs. When I look at the total install costs, I think it's also important to reflect that the total install costs are not only the equipment costs, but they also consider other costs such as civil or engineering or the contingencies. If we look at the and also depending on the technology and the project size, when we look at the contribution of the stack cost, and this, for example, this is an example from alkaline technology for a particular design. So you can see that it is about 15 to 30% of the total install cost. So these are significant contributions. Electrodes and membranes are the most expensive components of the stacks, and of course, cost reductions can be achieved by selecting less expensive materials or also less critical materials. Challenge is also to maintain the performance. We can optimize in the size of the electrolyzer module. Standardization of designs is also very important. Replicate as much as possible. Optimization of the manufacturing processes, and among other options, of course. Here I have an example of a study that we did a couple of years back, where we look at for a gigawatt plant, what is the state of the art, so the baseline, and the cost per, for example, per component, and come up with ideas of how we can have an advanced design, let's say something that technology-wise already can be ready in, let's say, 2030, and what is the impact on costs. And of course, I mean, the graph looks very nice because you see a significant cost reduction for both alkaline and PEM. But the challenge is not only to come up with these smart ideas for reducing the cost, but the challenge is to test these ideas and implement them at the scale, because there you also need to look at the how this is going to be manufactured, but also what is the performance, and also what are the implications on, for example, durability, degradation, and the impact of for example, the operating conditions thereof. If we look at the cost and performance, I think they always go hand in hand. So if you start with the choice of materials for key components, especially the electrodes and the membranes, also the operating conditions will dictate the performance of the electrolyzer. I have here an example of it's same supplier. It's a Chinese supplier. And they have in their portfolio two product types. So they have one that's it's about high energy efficiency, and the other one which is minimum capex. And besides the size of the module, I think the main difference with respect to performance is that on one, the very efficient one is of course has a lower power consumption compared to the one that has minimum capex. So there is always a trade-off of cost and performance, and when if we reflect back on the contributions of capex and opex in the LCOH, I think it's always a balance, or on individual basis, a project what needs to be optimized, because maybe, for example, in places where electricity is very cheap, you can optimize there. Maybe in some countries where you have to pay more for your electricity, then you optimize differently, of course. And I think it's also good to mention that in the market there are many electrolyzers manufacturers. Choosing one is not a trivial task. I think it really depends on the conditions that you have for a project as a general. And I think also one of the key aspects is that the technology maturity of the particular electrolyzer product needs to match the project risk appetite. And what I mean by that is that maybe there are new technologies that are not perhaps not thoroughly tested or not to the scale that one would like, but they are very competitive. So if a project can take a higher risk, then it will also make sense to investigate those options. Whereas, for example, if you want to really in a particular project, you really want to minimize and reduce as much the technology risks, you probably choose for a more mature technology. Now, when we look at the requirements from the RED II directive, green hydrogen is to follow the renewable energy sources profiles on an hourly basis. And what that means is that, so I have here an example of a wind profile. And what this means is that the electrolyzer needs to follow that load. And one of the aspects, for example, on the design and on the operations is that the electrolyzer has a certain minimum loads to a threshold at which the electrolyzer can operate safely. And here there are two examples. So, for example, a stack that will operate at or that can operate only until 40%, for example, at this point we'll have a shutdown. Maybe if it can operate at the lower loads, then the shutdown will be a bit less. And of course, shutdowns will also depend on how long is will the load stay under those conditions. And the effects on of this shutdown of the electrolyzers are not always well understood with respect to, for example, degradation, for instance, and also with respect to flexibility. I think is also key to realize that although you could argue that electrolysis technologies are very mature, but flexible operation at larger scale has not always been thoroughly tested. I think one example I want to give is, so there is this plant, there's a KUKA plant in China. It has stacks of 3 suppliers, about minimum load of 30% each, and they have reported issues with them, and these are related to the flexible operations, where the minimum loads stated by the suppliers was not even possible. So that means that the plant this has led to significant production losses. And when we think of how much green hydrogen costs, that's something painful for industries. So that's something to also realize. And another thing is, I think it was already introduced by Arend, so the gas crossover. So this is safety should be a key aspect to considering when developing especially large scale hydrogen plants. And we should not overlook safety. Gas crossover will have an impact, especially with respect to safety. So as we know, so hydrogen can leak through the separators, and besides loss of maybe production, but it's mostly on the risk of mixtures of hydrogen and oxygen. And key things to consider is so it's a complex matter. I think it depends on pressure, but also on the load, and of course the type of membrane, how thick or thin it is, or the type of the membrane itself. So there are a lot of elements to be investigated and to consider there. When I look at so when everything comes together, so I think in the market, as I said, there are a number of players there. They have different products available. They all have different technology readiness levels. I think that implementing large-scale electrolysis for the large-scale off-takers requires mature technologies. So typically with TRL of 8 or more. And one thing to consider is that I think we need to do innovations, and these innovations need to be tested. And often, for example, a manufacturer will change an electrode coating or a cell design. This needs to be tested at scale. So we need to the risk as much as possible and test at scale. And this is not always easy, because testing at scale can also be very expensive.
2 minutes, Paola.
Yes, thank you. So this is perfect timing, because this brings me to my takeaways for you. So I started by mentioning indeed that Europe has a very large ambitions to decarbonize industries, and I think we need to strive to achieve these ambitions if we want to meet our climate targets. The hard-to-abate industries will definitely make use of green hydrogen for decarbonization, but the offtake commitments are at the moment difficult because, among other things, there is still a gap between what the hydrogen currently costs and what the off-takers are willing to pay. This also brings opportunities for electrochemical engineers to develop more cost-effective but also flexible, safe, and proven electrolysis technologies, and there everybody can play a role. And with that, I like to finish my presentation and take some questions.
Thank you very much, Paola.
Mhm.
So I see 2 questions in the chat. The first one from Abdusalam Aladidi. Do you think that the availability and cost of fresh water required for hydrogen production will have an impact? I think water-related risks are higher than electricity. What do you think?
I think it's a very good question. I think that and it's not an easy answer, and because it will always depend on the local situation. So what we see is that at least for the projects that we have been developing, so far it has not been a challenge, but when we think about the ambitions of let's say 90 to 100 gigawatt of electrolysis capacity, this will definitely need to play a role, especially because we should not compete with water for drinking purposes. So therefore, we also need to invest time in investigating and finding solutions for use, for example, reuse of other effluent streams for other industries, or for wastewater treatment plants, or from seawater, etc. And so I think this is a very key aspect. Thanks for the question.
Thank you very much. The next question from Matteo Miola. How much the development of the industrial electrolyzer producers relies on published scientific advancement with respect to internal company benchmarking?
I think that so if I see what's the innovations that are done by the key players, for instance, of course, all the electrolyzer manufacturers, they have a very large, or at least they invest a lot in R&D, and they are preparing for the next generations of innovations. I think that at least that's something that I admire a lot in Europe, that there are typically very good relationships between industry and academia. And I think that a lot of the very good ideas that are coming from let's say from public or from academic sources will end up in applications on industrial level. But and I think therefore on the other hand, I think it's always good that academics take steps in order to link to industrial applications. I think at some point, everything, if you want to have something applied in the field, it needs to be commercially successful. So that's a key aspect.
Thank you. Next question, Julia Schwarte. How would you solve the fluctuation in the minimum load at a technical level? For instance, with the temporal energy storage systems or something similar?
Of course. So there are ways of balancing the, let's say, from the off-taker side to provide baseload hydrogen. This is very project dependent, depending on, for example, whether you have access to the hydrogen backbone, or whether you can, in your business case, you can allow for installing batteries, etc. So those are the, let's say, the balancing solutions, let's say, from the either energies, electricity or hydrogen side. And on the minimum loads, it can also be, I think one aspect to consider is how to operate. So the electrolysers, you can achieve a certain minimum loads of the plant by, for example, deciding to shut down more stacks and keep a few operating higher loads, and that will have an impact on your degradation, for example, and your performance, which translates to your business case, and that optimization needs to be looked at. So what will be the impact on the business case at the end?
Thanks. Next from Asif Ansar asks, how important are reverse current tolerance for alkaline in the context of intermittent power?
I think that's also, thank you for the question. That's also a good aspect to consider. I think that there are ways to prevent the issues related to reverse currents by, for example, installing the adequate electrical equipment to prevent that. Solutions there are expensive because electrical equipment often is. I think that looking at that from the cell design and from the stack design, it should definitely not be overlooked. Indeed.
Next from Guido Moel, do you know of technology implementation of alternative anode processes other than oxygen and chlorine?
That's a good question. I don't have an answer for that. I have to say that's not the field that I typically work on. Mm-hmm.
And the last question: what are your opinion of the response time requirements from a project developer for cold start and hot standby to nominal loads?
Can you repeat the question, please?
Yeah, the response time requirements for a project developer for cold start and hot standby under nominal load condition.
Okay, so what I see is that at least for the electrolyzers that are in the market, and you could argue, for example, whether how flexible and how fast are, for instance, alkaline compared to PEM technologies. If I look at what's currently in the market and what are the requirements in terms of how we need to follow the wind profiles, even the slowest alkaline electrolyzers can follow the ramp rates of the wind and other renewable energy sources. So I don't think that is a very big challenge from that perspective. So, but of course, it's an aspect that may play a role when selecting a technology.
Thank you very much, Paola. This was the last question, just right on time. So we're going now to continue. We're going to switch gear in the program, talking about CO2 electrolyzers. And I think there is no best way to start this with the next speaker, that is Dr. Czaba. Czaba obtained his PhD degree at the University of Szeged, and in 2014 he started his own research group in the same university that focused on materials, on system-level development and scale-up for both CO2 electrolysis and hydrogen production. So his team has developed different type of flow cells to test different reaction and catalysts at industrially relevant conditions. And Czaba is also the co-founder of eChemicles, that is a startup company aiming on scaling up the technology. So Czaba, could you please put your slides in full screen?
It's supposed to be that way, but if not, then give me 1 second again.
Yes. Yeah.
And then I will just do it again. Wait, sorry.
Take your time.
Well, how about now?
Yes, please go ahead.
Perfect. Thank you very much for the invitation and for the introduction. And this will be a little bit different compared to the previous talks. So there will be a little more fundamentals, but also hopefully some insightful information for the engineering community. So yes, what we are working on and what we are trying to do is to implement a circular carbon economy. So to use industrial CO2 sources and an electrochemical process, CO2 electrolysis, powered by green energy to generate different energy carriers, chemicals, or even fuels. And I won't be talking about alternative anode processes. There was a question after the previous talk, but we also work on connecting or pairing CO2 electrolysis with other processes other than water oxidation. So for example, glycerol oxidation, and then we can make the same product in both the cathode and the anode process, but that won't be the scope of today's talk. On the other hand, what will be the scope, and this slide was borrowed from TU Delft, because I just consider this slide to be very descriptive, that when we want to develop an electrochemical process or any kind of process actually for the chemical industry, the traditional problem or challenge of the scientific community has been that we have been focusing on these microscale processes. So catalysis, the electrochemical process, what kind of materials do we need? And there was a big mismatch or disconnection between the subsequent steps. So how we are going to ensure proper reactant transport and how to remove the products, how we provide the necessary power and remove excess heat from the process, what kind of reactor or cell development efforts do we need to invest, what kind of separation methodologies we need either upstream in terms of the CO2 purity or downstream in terms of the product gas stream from the electrolyzer cell, how we can integrate this into a larger process and how to control. And this is not a linear process. So it's not like, okay, we come up with a wonder catalyst and then we just put it on the line and then at the end we have the technology. So there are constant feedback loops on this journey. And this is something where I think we as a community need to do better in terms of collaborating with each other. And so with this purpose, and I just dedicate this one slide to this, we started a national laboratory program in Hungary a few years ago involving 12 different universities and research technology organizations, altogether 32 research groups, to be able to move this a little bit forward. So to move beyond this technology readiness level 3. So after having a proof of concept, to try to bring it to a larger scale, which is understandable for our industrial partners, and they can believe those KPIs, what we get for the different processes. And to do this, we dreamed first to have a test station, which we called Energy Conversion Innovation Test Bed, by having a small PV farm, the sunflower type PV following the sun, having a battery container where we can store some of the energy generated by this PV farm, having a power-to-gas container with different electrolyzer technologies inside, one hydrogen and one CO2 electrolyzer technology, and having a power-to-liquid container which can process the hydrogen and the CO made in this container to generate different liquid fuels. And so we started this construction now a year and a half ago, and the first was having these solar panels ready, and then the containers came. It's important that we designed these containers, and they were manufactured by contracted suppliers of us. So we first had the power-to-gas container, and then this is the moment when the power-to-liquid one was delivered. We had a nice opening ceremony during this summer. We cut the ribbon and now it's fully operational. And the reason why I'm mentioning this, that this is an open facility. So we have this not only for the purpose of testing technologies spinning out from our own university and country network, but it's all open to external partners as well. So if you have an electrolyzer stack you want to test, we can put into our system and perform different sort of testing. That's the same same for catalytic reactors or even catalysts. And this is something we are very much open to do, and we are already doing it with different partners. But this talk is dedicated to CO2 electrolysis and specifically CO2 to CO conversion. And the reason for this, that back in 2017, we picked this reaction because of two purposes. One is that we thought that technologically this is the most understood and most mature CO2 electrolysis process. And also it has a good market in terms of size, that there is not only a bulk market, but there are also smaller scale markets where we can enter to the market already with smaller scale devices. And back then we asked the question, what is really limiting the performance of this process? And so what we found is that it's by far not the catalyst, but at that time there were no proper electrochemical cells for CO2 electrolysis, except the high temperature solid oxide electrolysers, which have been around for a while, but that's a different story. It's not the topic of this presentation. If you think about low temperature electrochemical cells, then you can have many different options depending on if you have a membrane or not. So it's a simple microfluidic device or membrane-based device. If you have a membrane, then you can have systems where you flow liquid electrolytes on both the anode and the cathode side. If this is the case, then you use CO2 saturated catalyte. These are not very efficient because of the limited solubility of CO2. So typically the field uses gas-fed electrolyzers with gas diffusion electrodes, because then the CO2 can be properly distributed and fed to the catalyst surface. And in our studies, we are focusing on this so-called zero gap design, which is very similar to fuel cells or PEM water electrolyzers, where both catalyst layers are pressed to the membrane. There is a porous transport layer on the anode side, and there is an anolyte, but there is no catholyte. The CO2, humidified CO2, is directly fed to the cell. And so already 5 years ago, we came up with this stack design. In fact, we prepared, or we designed two types of electrolyzer stacks. One is the classical one, where we feed CO2. It's uniformly distributed among the different cells in the stack, and then the product is collected in one product stream. For the sake of curiosity, we also designed another cell, which we call serial cell in terms of gas management, where the CO2 feed is forced through multiple cells. This is not a classical way of operating an electrolyzer stack, but with this we can do interesting chemistries. So for example, in the first cell we can do CO2 to CO conversion, and in the second cell we can do CO to ethylene or other processes. And again, as a reminder, so one cell looks like in a way that there is a porous gas diffusion layer through which we feed the CO2, which meets the catalyst, which is pressed to an AEM in this case. And on the anode side, we perform water oxidation with a low-loading iridium electrode immobilized on a porous titanium frit. And even back then, 4 years ago, we got reasonable performance, so around 600 milliamps per square centimeter partial current density for CO formation, 35-40% single pass conversion of CO2, reasonable durability. And if we increased the CO2 feed rate, then we were able to go over 1 amps per square centimeter. But the key message here, and that was also echoed before for the hydrogen, but it's even more amplified in the CO2 case, because there is also a selectivity question which doesn't show up in the hydrogen case, that all these KPIs like current density, energy efficiency, single pass conversion, durability can only be considered together as one holistic mix of KPIs. Because if you check the literature, you will see beautiful papers in Nature Science claiming record high efficiency in one given parameter, but then you read the paper in depth and then you will find that they have homeopathic single pass conversion, for example, but a beautiful energy efficiency. So it's very important to consider all these parameters together. And at this point, so this was a nice proof of concept that, okay, these zero gap designs can work. We can perform this CO2 to CO conversion. And at this stage, we only used commercial components, so commercial AEM with the ionomer, commercial catalyst, commercial GDE, basically, which we picked as a first instinct. And since this moment, we started to systematically study the role of different components and started an optimization process. And I will just show one example here for this component optimization. And this is for the carbon support for the cathode catalyst, so this carbon gas diffusion layer. So what we did here is we purchased 20 commercially available carbon gas diffusion layer and assembled electrolyzer cells absolutely identically. The only factor changing was this carbon support. So same membrane, same ionomer, same catalyst loading, same cell, everything was the same. Same operational parameters. And what we have observed that the performance is day and night. There were cells which almost exclusively generated hydrogen, no CO. And there were others where almost only CO was generated, no hydrogen. So this clearly signaled that already one component, this carbon gas diffusion layer, can play a key role. And then we grouped these carbon papers into different categories to draw some conclusions. One conclusion was that indeed we need a microporous layer on top of this carbon, because without the microporous layer, we can't get selective operation. But with the microporous layer, it works well. The microporous layer cannot be substituted by adding more Teflon or more hydrophobic agents into the electrode. You really need that microporous layer. We also show that the thickness doesn't really matter. So in this range between 200 and 500 microns, we saw very similar performance, and we have seen some morphological effects. But long story short, even in this case, it was crystal clear that even with identical parameters, just by changing this carbon support, we can get very, very different performance. And actually this signals, or this is a little bit worrisome, because if you read the literature and you read those hundreds of papers of new catalysts being studied and showing very little difference in performance, and then you check that in one case they use one carbon and in the other case they use other carbon, and you get much bigger differences even with the same catalyst just by changing the carbon. So it's something about the system aspect and system engineering and understanding that it's not the catalyst alone. The other thing we have been paying a lot of attention is the electrolyte balance and identifying the complete mass balance of these processes, because 5 years ago, this was the common understanding of the field, that you feed humidified CO2, you generate some CO, there is some unreacted CO2, there is byproduct hydrogen, and at the anode you generate oxygen. But quite early, it turned out that this is not quite the case, because you have a highly alkaline environment at the cathode, you dissolve the CO2, and as we are working with an AEM, there is, depending on the current density, which dictates the local pH at the cathode, you have either carbonate or bicarbonate conductivity instead of hydroxide conductivity, which results in a CO2 carbonate crossover, which is liberated at the anode. And this limits basically your single pass conversion, because with every molecule CO2 converted, you are pushing through one molecule of CO2. This is not detrimental, so this CO2 oxygen mixture can be separated and CO2 can be recirculated. It's a cost item which has to be factored into the techno-economic analysis. What is a little worse is that no AEMs are perfect, so there is always some sort of cation transport from the anode side to the cathode side, and because of the highly alkaline environment at the cathode, having these alkali metal cations cross the membranes or the membrane, you can have precipitate formation at the cathode, which is detrimental for the operation. So this is important to avoid having too much cations in the cathode side. So here came the idea, why don't we use simple DI water at the anode? We have iridium catalyst, similarly to PEM water electrolyzer, so it should work. And then surprisingly, we found that if we use pure water on the anode, then we have very low current densities. That's always the first part of these curves. So we thought that we might need those cations at the cathode as promoters, because there were indications in the literature from theoretical studies that you need those cations as promoters. So we thought, okay, let's operate with water at the anode, but let's bring on purpose these cations to the cathode compartment. So we developed the protocol with a proper solvent mixture to inject these cations to the cathode. And indeed, it works with different membranes. Once we inject this activation solution, then the total current density jumps, and also the CO partial current density jumps. So we were able to mitigate this issue by purposefully introducing these cations. And we have also shown that this is fully reversible, so you can introduce those cations, then you have high current density, you can wash them out, then you have low current density, and so on and so forth. And we also uncover the dynamics of this. But this raised the point even that time that electrolyte management in these systems is very intricate, and it depends on a lot of different parameters, like cell design, cathode gas parameters, anolytes, current density, cell voltage, and so on and so forth. And these dictate the ion management as well as the overall performance of the cell. And what we found is that these are all interconnected. They all affect each other. And I had the impression with my colleagues that we have reached the limit of our chemical intuition. So we teamed up with a group working on machine learning to find the optimal operational conditions for these systems. And so they came to us and asked how much data we have. And then we told them, then they started to laugh. I told them there is nothing funny ongoing, and then I want to work on this. And then they said that we should generate more data. So we started to build up these automated test stations. And this was the first generation where we had 4 cells next to each other, working completely independently. And we can change all the operational parameters on this. And so what we do here is that with different operational parameters, we gather experimental data, we filter it, remove some outlier points, process it, and then we get a data set. How this works, we vary basically parameters like current, gas humidification, cell temperature, CO2 flow rate, and the anolyte concentration. And by trying different combinations, we check the output parameters, which are the cell voltage, selectivity, single pass conversion, and these kind of parameters. And we built a model, a neural network based model. But before I get to that, I just show that we vary all these parameters systematically and then define protocols having these parameters varied in the range where we want to study it. And basically, this is just one example, running a CO2 electrolyzer cell for 24 hours in this case. Every half an hour, different kind of operational protocols. We are following how these parameters are changing, like the cell voltage, the selectivity, in this case, the CO to hydrogen ratio, single pass conversion, and for example, the pressure which is building up in the cell. This is an indication, for example, of precipitate formation when we see the pressure building up. So there are operational circumstances which are not favored. And what is very important in this case, that by gathering data and building these models, we can very, very nicely predict the values which we expect from the operation. So for example, in this, it's a single pass conversion. The blue is the experimental data. The orange one is the predicted data by the model. And now we are using this as predicting future failure modes and to intervene in the system before the operation goes wrong and it behaves in an unexpected way. And also by optimizing this data, we can now routinely run these cells for thousands of hours. And that way we can determine degradation rates. And I know for people coming from the hydrogen community, these numbers look high. They are about 5 to 10 times higher than what you expect from, let's say, a PEM water electrolyzer. But I have to tell that 3 years ago, we were an order of magnitude higher than these, and we are improving rapidly, and we see where we can improve this further. And we have really good hopes to get to those numbers which are expected for durable operation. One thing which is important also to mention, that it was all mentioned before, that intermittent operation and dynamic operation is important, although most of the end users on the downstream, both for hydrogen and CO, need 24/7 operation, but it's good to have the opportunity at least to operate in a dynamic way. Actually, we were the first one showing that you can operate this kind of CO2 electrolyzers in a dynamic manner, and it's not for granted, so it really depends on the cell architecture. We have shown in this paper that some architectures are good, others are not. First, we started with a simulated protocol, having a fixed baseline current density and a fluctuating current density. And this is just 500 hours data. The part where we have fluctuated the current, the part where we have shown a stable current, and it works very nicely. And then we also connected this to a solar PV for a week in this case, and showing that the CO production is nicely following the load. And I see Michele, so I will wrap up quickly. A few words about eChemicles, the company we started 2 years ago to translate these results, these proof of concept results to the market. And so we did scale up from the 8 square centimeter through 100 square centimeter to this 2,500 square centimeter single cell. Now we have this stack with 18 cells in the stack. This is how it looks like. These are the KPIs we are targeting with this system. And actually we are very close to getting it. It's over 92% Faraday efficiency for CO. We are around 3 volts cell voltage. You can already see that you have 1,000 amps going into this stack. So this is already quite something. And with further improving the components, we can go up to higher current densities. This is 600 milliamps per square centimeter in this case, still around the 3 volt cell voltage, and having over 95% selectivity for the CO formation. And we have our first prototype container shipped to our site actually last month. Commission is ongoing, and what is a message here for the community that next spring in April or May we'll have a stakeholder workshop for CO2 electrolysis when we'll show our container in operation on our site. And to conclude with, same slide which I started with, I think it's very important to highlight that professionals throughout this value chain need to cooperate in order to bring technologies to the market. And with this, I would like to thank you for your kind attention.
Thank you very much, Czaba. A lot of information, very remarkable results. The first question is more of curiosity. How many people were working on this full time in the past 5 years?
Well, I would say about 20 to 25 altogether. Now we are growing. Now we have 30 people at the company.
All right, thank you. The next technical questions. What is the mechanism by which the GDL makes a zero gap cell more selective for certain gases, even though the catalyst stack remains the same?
Yeah, this is a very interesting, this is a local chemical environment. So how the local chemical environment changes, that really depends on both the CO2 transport, water transport, and that's heavily affected by the morphology and the hydrophilic, hydrophobic nature of that catalyst carbon interface. And simply this is the local chemical environment develops in a way that you need that microporous layer there. And
do you know was this mechanism verified?
No. That's one of the big questions.
Yeah.
Actually this has to do, and that's maybe an interesting message for the community, that when this whole gas diffusion layer architecture concept was born, then this triple phase boundary like catalyst, gas, CO2, liquid, water, electrolyte was introduced basically, and it's quite challenged at this stage, I would say. So nobody really knows whether there is a triple phase boundary or there is just a double phase boundary with a very thin electrolyte layer on the catalyst, and then the CO2 gas needs to diffuse through that very thin layer. And if this is the case, if there is no triple phase boundary, just a double phase boundary, then it really matters what's the morphology of that layer where you have the catalyst immobilized.
Thank you. So next question from Ahmed Zafar. What are your views on a dual ion conductors electrolyte, like proton and oxygen?
I'm not sure.
Dual ion conductors electrolyte, like proton.
I think those are the
oxygen.
high temperature. That's for the high temperature electrolyzers where you have those ceramic conductors. Yeah. That's not the case.
For having O2 minus, it's about high temperature, and your talk was about low temperature CO2 electrolysis. next one from Lucas Cino. Did the intermittent operation that you show have any significant impact on the durability and stability?
Not at these time scales, but we are now studying what's going on longer time scales. Interestingly enough, what we see is the more challenging part is the anode part in these durable operations, because these AEM-based anodes are not as robust as the PEM-based anodes, let's put it that way. So there is room for improvement there.
Thanks. Next from Guido Mu. What is the difference in the diffusion rate of hydroxyl and bicarbonate or carbonate through the membrane?
It really depends on the membrane, what kind of membrane. This one, which we use, this Piper ion, this has very high conductivity and diffusion rate for carbonate and bicarbonate. And in fact, that's why it works very well in CO2 electrolysis. So we have tested membranes which are very good for OH conductivity, but they are not good for carbonate. But in this case, this is good.
Can you give a ballpark range of the ratio between OH and bicarbonate?
Well, what I can tell that in this case, it's quantitatively, I mean, depending on the current density where you operate and the CO2 feed. But in our case, it's quantitatively carbonate conductivity.
Okay. Next one, why not use PEM membranes? Won't that solve the carbonate issues?
It would. But then you will have very severe selectivity issues because then the local chemical environment will be acidic or not alkaline, at least on your cathode, and then you will generate hydrogen instead of the CO. In principle, you should choose you should exchange all these cation exchange membranes instead of being proton exchange to other cations. But then again, you will have very high cation concentration at the cathode, and you will be forming precipitate because of that, not because of the alkaline nature, but because of the very high cation concentration. So there is always a trade-off. So it's there is no perfect. These are the problems of the AEM, the carbonate crossover, but that's a cost item. How much does it cost to separate the oxygen from the CO2 and recirculate it? You can use bipolar membranes, and that's a big research field now. And with properly designed bipolar membranes, in principle, you can have the best of the two sides. You can have good conditions for the anode process and good conditions for the cathode process, but then you always have an energy penalty in these bipolar membranes. They are running at higher cell voltage. And I'm not saying that won't be the solution. That might be an elegant way of tackling this issue. But the energy penalty have to be compared with, let's say, the cost of the gas separation in the AEM case.
And is degradation the main bottleneck for further development? And at what level this could be solved?
I think yes. So basically, I believe that's the biggest challenge at this stage. What we see is that there are many different types of degradations and performance fadings. Some of them are trivial and they are occurring already at the few hours time scale. Others are more intricate, let's say few tens of hours, and then you get to the 100 and 1,000 hours regime. So, for example, where we are now in this few thousands hours regime, we already start to see those kind of degradation mechanisms, what you have in the hydrogen community. But I think the CO2 field in general has to get there and to be able to study. And we would need accelerated stress test protocols. That's the other thing, which is completely missing. Now we are discussing with the European Innovation Council to start a project on that, actually, to have some sort of AST, at least to test different AST protocols, what is possible, because I mean, we are running these cells for these 2,000-3,000 hours, but our capabilities are limited, so we can't run so many of them at the same time. And it would be really good to see what is a good AST. And I think also the hydrogen field is having troubles with this. For the fuel cells, it's okay maybe, but for the electrolyzers, there is still no consensus as far as I understand.
Yes, indeed. In view of the time, I will read only the last question, and I would like to ask you to answer the next two in the chat. So, do you think Piper ion is better than Sustenion? Why?
Well, I mean, I don't want to be a commercial person, What I can tell in general, that AEMs for CO2 electrolysis developed tremendously in the past 3 to 5 years. 5 years ago, there were very limited choices, and now there are much more, and overall the quality is much better, and especially in those companies which entered to mass or semi-mass production of their membranes, and Piper Ion is one of them.
Thank you. I would like to ask you, Czaba, to reply to the question in the chat.
I will do.
Thanks.
Thank you very much.
Thank you again. And then I'll move on to the next speaker. Gareth, could you please already start sharing your slide? So Dr. Gareth Williams from Johnson Matthey. So Gareth is a senior process engineer at the Johnson Matthey Technology Center in UK. And he's in his role at Johnson Matthey, he provides chemical engineering support towards feasibility of novel electrochemical processes. So he's definitely the best person we could find, and one of it I can think of to follow up on this discussion, more looking at from a manufacturer point of view of the electrodes. Please, Gareth, the floor is yours.
Thank you very much, Michele, for the kind introduction. I'd say follow on from Czaba's great talk on the electrochemical reduction of CO2 for sustainable fuels and chemicals. I'll try and give some perspectives as a chemical engineer into this as well. So the outline of my talk today, so I'll briefly introduce JM, highlighting that we're active in the electrochemical technologies of PEM fuel cells and PEM water electrolysers, developing and supplying the critical components for them. And then I'll look at what we're doing at our technology center, where I'm based, on CO2 electrolysis, and then give some considerations and challenges for the future development and deployment of CO2 electroreduction technologies, and then wrap up at the end with some final thoughts as takeaways. So JM is committed to addressing the 4 central transitions needed for a net zero future. So namely transforming global energy systems, decarbonising chemicals production, driving down automotive emissions, creating a truly circular economy with the recycling side of things. Underpinning this is sustainability, and our products go to help our customers achieve their sustainability goals, as well as in our own in-house manufacturing operations as well. Just sustainability is key. So our business structure aligns around our 3 key markets of automotive, chemicals, and energy. First, we have the clean air business. So we supply catalysts, auto catalyst technology to clean up the emissions from diesel and gasoline vehicles. Catalyst technologies, looking at catalysts and licensed process technology to decarbonize the chemical and energy industry. Hydrogen technologies. So we're looking at the critical components of PEM fuel cells and PEM water electrolysers there. And these 3 businesses are underpinned by our Platinum Group Metal Services business, which is a key sort of secondary refiner of the precious metals, as well as looking at providing end-of-life recycling solutions to our businesses. So our structure sort of capitalizes on mutual partners and customers between the businesses and our shared technology capabilities. And as I mentioned, it has the foundational PGM ecosystem, which is very relevant to all the businesses as well. So now I just focus on the electrochemical technologies where we have businesses, namely the PEM fuel cells and the PEM water electrolysers. And as I say, we've got decades of experience in the PEM fuel cell side of things, and naturally that will transfer to the learning for our up and coming PEM water electrolyser business with the critical components, and then hopefully in the longer term into CO2 electrolysis as well, which is still in development. So just on the PEM fuel cell type offer, we're quite unique in that we manufacture and sort of supply both the catalyst and the membrane. And we also offer the recycling option as well for a spent component for our customer as well, increasing the sustainability aspect. So we can coat the precious metal on the catalyst, on the membrane, so using the PGM platinum anode cathode, and produce a catalyst coated membrane. We can then add seals to this and produce a sealed catalyst coated membrane, and then add the gas diffusion layer, and this goes on to form the membrane electrode assembly, depending on what our customer requires. And the customer can take the MEA and make a stack, a fuel cell stack, and that can go into vehicles or stationary fuel cell applications. Many stacks would go into a truck, for example. So in terms of our electrolytic hydrogen side of things, where we produce the CCMs, which are similar to the PEM fuel cell type CCMs, apart from the anode, it's iridium based, whereas the cathode is typically going to be platinum based. So we produce this sort of optimized CCM for our customers. And in this area, we're looking to optimize our CCM by taking into account the reducing the levelized cost of the hydrogen and ensuring the availability of key materials. So we're looking to optimize with the trade-offs across the areas of efficiency, durability, and the capital cost. And as I mentioned, the word trade-off, that comes into play, and we need to manage these with our customer to get the latest sort of state-of-the-art product that the market requires. So these trade-offs I mentioned are linked technically to like a membrane thickness, catalyst load-in, and also component cost. For example, having a thicker membrane has its pros and cons. But I think these sort of trade-offs do sort of would transfer to a CO2 electrolyzer as well that we need to be mindful of. So I'm based in the electrochemical transformations team in our tech center. This is led by Krina Korbos. And we're looking at new opportunities for Johnson Matthey in electrochemistry beyond hydrogen, beyond our sort of fuel cells and green hydrogen water electrolyzers. So the question is, how can electrochemical CO2 fit in with our existing technologies? So we have a suite of sort of thermocatalytic technologies which take CO2 and make sustainable eChemicals, e-fuels. Via a syngas. So we can apply our FT cans, which is Fischer-Tropsch sort of technology, or methanol synthesis technology. And so the water electrolysis providing the hydrogen, so power to X type scenarios there. You can also generate the syngas via low temperature electrolysis and also high temperature electrolysis as well. But also from the low temperature electrolysis, you have these other markets that were opened up to make directly ethylene, ethanol, for example, formic acid, some of the products you can make from CO2 electroreduction, which is interesting. And as we mentioned in the earlier presentation, talk about increasing the energy efficiency of this electroreduction by having an alternative anode reaction, a selective oxidation, instead of producing oxygen, which is generally just vented and as low value. So we can look into that as well. So it fits in our strategy of interest. So this stylistic slide sort of tries to answer the question that electrochemical reduction may not be the best choice of technology, and it all depends on what target molecule you want to make from CO2. So it looks at the carbon oxidation state of the product and the carbon chain length. So in blue, you got the thermocatalysis type technologies. Orange is electrochemistry and biological in green. And what I think you can conclude by this sort of map is, I think for lower molecules, lower chain molecules, so the ethylene, COs, electrochemistry is suitable, and that sort of competes with the thermocatalytic routes as well. But for longer chain, you'll probably need a multi-step process or hybrid. Or also some maybe biological type routes as well to reach those C5, C6s with more oxygen content as well. So as you say, there'll be a mix of technology options depending on what target molecule you want to make from the CO2. So I'll briefly sort of talk about the CO2 electrolyzer, how it works. It's similar to, sorry, I've moved on one. It's similar to a water electrolyzer in some areas. So CO2 is introduced at the cathode, where it reacts with a source of hydrogen, and then it gains electrons from the process. Electrons are generated at the anode, producing oxygen and conducted by the external circuit back to the cathode. So the electrocatalyst will depend on the targeted product. C2 is typically copper-based, and at the anode, you either have iridium-based for acidic type electrolysers, or transition metals, obviously keeping away from the PGMs for alkaline conditions. So when I looked at this, I think this is heterogeneous catalysis. So familiar to a chemical engineer, the surface reactions, the mass transfer of electroactive species, and the bulk reactants moving between the electrodes. But it also requires understanding of the ion transfer at the interface of the electrode, and the charge transfer, sorry, at the interface of the electrolyte and the electrode as well, that needs to be added. Right. So at JM, our focus at sort of R&D level is on development of the catalyst materials and the catalyst layers. So hopefully getting to a product of a CCM, as we do in our hydrogen technologies business. So catalyst synthesis, so optimize inks for the coatings, and then different deposition techniques, and then we have some test capabilities as well in-house. And so various stages in the process, we'll characterize the products with our in-house suite of analytical instruments. So JM is a sort of innovative company, and we participate in collaborative research. So the following projects here are EU projects funded by Horizon 2020 program, and these are in the areas of sustainable fuels and chemicals using electrochemical production technologies. So we participated in these ones. They've all finished. I just wanted to highlight the results from the EcoFuel project. In this one, we have Johnson Matthey supplying some copper oxide catalyst, which was down selected in a 10 centimeter square CO2 unit by Siemens Energy. They then went on to do a stability test using the catalyst in an optimized electrode, and they achieved over a month of uninterrupted stability testing towards ethylene, albeit at a fairly low current density, which was very encouraging. Johnson Matthey then sent some scaled up electrodes with the same copper-based catalyst. So they're 300 centimeter square electrolyzer at sort of TRL4 level we're talking about here. And they realized, so this electrolyzer consisted of five cell stack system, and they realized greater than sort of 80 hours, but it was still going. The problem is the project ended, so they needed to stop the run, the experimental run. So it didn't achieve more there. But there's some information in the publication. So now I just wanted to talk about some of the challenges from the very start, from the outset of CO2 conversion, and relate to some of the thermodynamics. So converting or reducing the carbon dioxide, either sort of electrochemically or thermochemically, in fact, it's very difficult, and that's partly due to the double bond of the CO2, the CO bond. But CO2 also exhibits the highest oxidation state, +4 of the carbon in many processes. It's like the end product and very, very stable. And I think it's displays the least energy in any sort of binary neutral carbon containing product as well. So the higher, less negative. So you see in this chart here that gives free energy, the higher or less negative reduction products that you can get from CO2. And that reflects the stability of the CO2 compared to the products, and acts as a sort of driving force. So the bottom line is, I think the large energy requirement will be reflected in any sort of techno-economic evaluation that you do for the conversion of CO2. It's always going to be a struggle there from the outset. And then staying on the subject of CO2, of the thermodynamics, we look at the half cell reduction potentials for the different CO2 reduction products. So I've got 7 products here in this table. I think there was about 16 that's been reported over the last 12 years or more, many at very low levels though, sort of thing. So these are the ones produced at significant levels at the moment. And what you can see here is the electrode potentials that are fairly close, especially, and you got this hydrogen as a reference, is also a competitive reaction. So the selectivity can be a challenge there, which is where the electrocatalyst comes in and any associated components of that to manipulate the over potentials or whatever for a desired product. So it's all about the electrocatalyst. So this next slide, it's process efficiency starts at electrolyzer cell. Yeah, as an engineer, I'm sort of very interested in the process efficiency of the plant. And we look here at the energy conversion efficiency at the stack level. So it can start at the stack. It will be higher because of all the balance of plants or whatever like that, but the starting point could be at the stack level. So I plotted the energy conversion efficiency for the different CO2 reduction products as a function of the Faradaic efficiency, like selectivity of the product. And what you want, as you say, you want to increase that process efficiency because it can impact on the OPEX as well as on the CO2-based emissions as well as your process. So you want to get that efficiency as high as possible. And the imbalance of the efficiency by operating above the minimum thermodynamic voltage and also below 100% Faradaic efficiency manifests itself as low-grade heat as well as byproducts that needs to be accounted for. So if you want to maximize the sort of Faradaic efficiency and minimize the operating cell voltage to boost your energy conversion efficiency, there's this trade-off to consider. We're getting the right current density, the reaction rate, which itself impacts on the capex side of things. So there is a trade-off there between operating voltage and current density, which all links together. And I just pointed out, I think CO, you can see from the chart, CO and formic acid exhibit the highest energy conversion efficiencies. And then in practice, from experiments and startup companies looking at this, they tend to also exhibit the best figures of merit in practice with the Faradaic efficiencies and current densities, for example. So they're the lower hanging fruit. So other considerations we have, how much renewable electricity is required. So I've looked at the power at the stack level so plotted that on the y-axis against the production rate for the 7 different CO2 reduction products. And what I've done is highlighted what you can get for 100 megawatts applied at the stack. And so formic acid is one example. So you can get over 700 tons per day theoretically. That's too big probably for formic acid plant, which is a niche industrial chemical. Probably 100 tons per day is more suitable. But on the contrary, for something like ethylene, you only get about 75 tons per day. And world scale, ethylene plants tend to be thousands of tons per day. So you need a bit more power, unless there is a market for small scale ethylene. And then the comments at the bottom, the system power requirement would be higher still due to the losses in the power electronics, but also electricity consumption, the balance of plant equipment such as separation and compressors and things. So the other consideration I have is how much feedstock is needed. So stoichiometric mass balance of the CO2 consumption on the y-axis against the production rate. And this can tell you how much CO2 you may need to capture from existing power plant or chemical plant, which sometimes could be thousands per day. So for your electrochemical plant, you may only need a portion of that. Also tell you what size DAC unit you need if you want to capture the CO2 directly from the air. And also the opportunity of the CO2 emission reduction. I mean, ethylene consumes more per unit mass of CO2 than something like formic acid would. So you look at your opportunity for CO2 emission reduction in your chemical product. So now we have a consideration to look at the whole flow sheet, I think, rather than just the electrolyzer in isolation there, because it's all about the profitability. So electrochemical process will generally require feedstock preparation, purification. You got the product separation downstream as well. There's also pumps and compressors to think about. So what that may look like for electrochemical plants, so you got the CO2 capture at the front end. So you got your electrolyzer, but downstream you got the gas separation and liquid separation of the products, and also recycling of any unreacted CO2 and liquid electrolyte back to the electrolyzer. All adds up in the capex and opex. And one thing talk about downstream separation costs, these can be significant, but they can influence the requirements of the electrolyzer performance in terms of what you need for selectivity and conversion. I've seen some publications in the literature looking at that aspect. So recommendation to perform the techno-economic assessment, I think early on, at the early stage, kind of puts a stake into the ground what the costs of the process looks at. And then it also sort of, it tells you where there's merit further development and investment, but it also can identify sort of technical performance parameters of your electrolyzer as well, where it be selectivity, conversion, or whatever. So I recommend sort of doing the techno-economic assessment early on, even though it has a high error margin at that point. You can refine it later as the technology develops with more accurate data. I mean, that goes similarly with the life cycle assessment side of things as well, to get environmental metrics, CO2 footprint, for example. And lastly, a note on renewable electricity and the utility side of things. So these parameters often profound effect on operating costs of the process. So as I say, the renewable energy is generally coming down, but the quoted as the levelized cost, and that's sort of an average of the electricity cost per unit or over the lifetime of the utility. Also, so it indicates the minimum sort of price at which it needs to be sold at, electricity, to break even. So my question is always, how much would a chemical plant operator pay for a long-term supply, 10, 15, 20 years via a purchase power agreement? How much more would that be than the levelized cost? And in terms of the capacity factor, not operating your electrochemical plant 24/7 because the power supply intermittency will lead to the higher production costs due to the fixed costs. So just some final thoughts now, just to wrap up. So Johnson Matthey provides technologies for decarbonising the production of chemicals and fuels, including e-fuels and e-chemicals. At our technology centre, we're looking at CO2 electroreduction, like collaborative type projects, focusing on the development of the critical electrolyzer components, electrocatalysts, the CCMs. And then lastly, I think engineering considerations reflect both the electrolyzer and the whole process flow sheet, and it's prudent, to look at the economics early on, with a case of homing in on a viable business case and profitability. And with that, I thank you all for your attention.
Thank you very much, Gareth.
Thank you.
Thank you. I don't see open questions in the chat, so I get my chance to ask first question.
Certainly.
So the plot you showed on the process efficiency stack level, very interesting. Is that based on actual data?
No, that was like voltage efficiency times Faradaic efficiency.
Yeah. So
yeah,
it was
2.5. Sorry, I assumed 2.5 volts. I assumed a voltage, actually, a typical one, which is fairly optimistic in the future, a future scenario. But yeah, I assumed it was not on experimental data. So what I wanted to do with that is just give you an idea of the sort of efficiencies that we have, and I referenced water electrolysis there as well.
So okay, it's based already on some optimistic assumption. So do you think this is right, the picture we will get in the future, or can we get anything better if technology advances? So how do you foresee this?
Yeah, to bring, as you say, it's, as I mentioned, it starts at the stack level, this efficiency number. So if you bring down the cell voltage, I think that's a challenge in itself, because a lot of the work is above 3 volts to generate appreciable sort of current densities and things like that. So 2.5 volts is already a big challenge side of things. Faradaic efficiency is the other one, which for some like CO and formic acid are like 90% plus. So that's good, but for something like ethylene, it's got some way to go. It just spells out the challenge, I think, that needs to be done. Some of the cell architecture as well, get into the zero gap side of things. We reduce the ohmic resistances and the overall cell voltage. There's that aspect. I think these things developed in unison. It's not one single factor like the electrocatalyst that's going to conquer it, or it's sort of optimizing things together. But it will be challenging. It'd be nice if you could get some of the KPIs, the figures of merit, similar to water electrolyzers. I'll be honest, but I think that's far into the future.
Yeah, thanks. I see questions popping up. So the next one is, which product makes more sense from your analysis for GM and your catalyst development?
For GM, probably the syngas side of things, because I showed you on that map, on that sort of where does the technology fit in. Syngas is the heart of our thermocatalytic type technologies. So producing sort of CO and sort of syngas. You've also got the high temperature electrolysis as well, the co-electrolysis, which is up and coming to consider. So that would be the first one. We're not active in ethylene at the moment as a market. So these are all future opportunities to think about that we're doing. But as I say, a lot of our sort of research work has been collaborative anyway with other partners, just to test and build our own in-house competency. But what we hope is, JM, is we can learn from our sort of fuel cells and water electrolyzer component business if the marketplace presents itself.
Thanks. Next question from Tai Nguyen. What is the key component challenge for industrial CO2 electrolyzer? Your view.
The key component. Well, it's not the raw materials. I'm just thinking what it's not. I think the iridium will be okay, as I say, linked to water electrolyzers. The copper, if you're going to go to C2 and couple in reactions to get the higher hydrocarbons, that's okay. Scale up. I think, as you say, you got to take each stage as it comes with the scale up side of things, and keep that uniformity. But it's manufacturing these things at scale. And they still retain the the technical performance. That's always going to be a bit of a challenge. But as I say, we've got years of learning from our other businesses at JM.
So what about then stability and durability? Basically, from your track record, how do you see that?
Yeah, that's got some way to go. Stability in particular. I mean, if you try and chase after water I think the water electrolyzers give a good target. What their targets are in terms of stability. I don't know, say 70,000 hours sort of thing like that. We're a long way from that at the moment. But yeah, stability is key, because that will dictate on how often you want to change out your stack on your plant. Say cost. This is where it comes in the techno-economic analysis to sort of pinpoint which are the most sensitive areas that you need to sort of improve upon.
Thanks. Next question from Vinod Pudiapura. What's your thought on AM and PEM-based CO2 electrolyzers?
Well, PEM-based is good, but they have the challenge. I think there's some challenges there. AM is less well developed, but we're also looking at that both of them in our water electrolyzer business as well, side of things. So AM is up and coming behind the PEM side of things. I think it's good, but as I say, the stability side of things need to be improved upon.
And then what about downstream separation for reaching industrial CO2 electrolysis? Are there any unknowns there?
I think, yeah. I mean, something like formic acid as a product is not sort of straightforward to separate side of things. There have been publications in this area. I think you can use some mature technologies like distillation, pressure swing absorption to do some of these separations. You've got to be careful in terms of the cost if you go into the cryogenic side of things. Maybe with ethylene type processes, and the costs of that. You may need some upstream compression, which is another area as well. All these cells are sort of operating close to ambient sort of pressure conditions. You may need some downstream compression to affect some of the separations, pressure swing absorption, for example, and these all need to be accounted for. But it is just as important as the electrolyzer itself in terms of the technology development, I feel. That's why I sort of emphasize the whole flow sheet.
Well, I 100% agree with this. We're also doing some study TNO on this point.
Yeah, you also got the upstream side of things as well to consider, and say impurities is always the question, both the CO2 and the water, because that would add to the costs and requirements. Are we talking about ppb levels of impurities or ppm levels? It makes a difference in the cleanup, and obviously that impacts on the stability, lifetime, and things. So.
The next question is from Max Berkers. Given that solar PV levelized cost of energy has fallen to such low levels, do you foresee many electrochemical plants and the chemical industry mass migrating to sunnier places like North Africa and Australia?
Yeah, well, why not? I think the location is very key for these sort of technologies. At the same time, there is this capacity factor argument that even if you're running your plant 40% of the year, if your solar PV is available, then without battery storage, it's still going to be expensive when you do the techno-economics. So whether there's need for battery storage or some way to smooth the energy, the electricity supply, or this grid, if you connect straight to the grid somewhere. And you got to maybe take the hit if there's some fossil fuels in that grid as well, because ultimately it comes down to the emission factors of the electricity supply. And I think that's where the power purchase agreement can help to smooth things. If that has a mix of electricity generation technologies within it and things like that. But yeah, it will be locational. It's where everything aligns. What's right in one location, what won't be replicated everywhere. So yes, no. I think it will be geography based.
Solutions are local then.
Yeah, especially the demonstrations side of things in the beginning. Yeah.
The next one is why ambient temperature? Can we operate at 60, 80 degrees? The electrolyzer.
Yeah. As far as I know, yes. I'm not working in the lab specifically and stuff, but yes, I don't see that's a problem for these low temperature electrolyzers like PEM water electrolyzers.
Yeah, I think the bottleneck is there. It's still the stability of the membrane. So indeed, probably 70s, some limits.
Exactly. Yeah.
Thank you very much. I think that was all, and also right on time. So I would like you can stay with the camera on. I would like also all the other panelist speakers. I want to ask them to put a camera on. So we're close to finishing. So thank you all for your contribution so far. Let's spend the last few minutes for some wrap up. In the meantime, feel free for the audience, feel free to continuously use the chat to ask questions, either to specific speakers or to the panel as a whole. And in the meantime, questions are popping up. I would like us to open up the conversation with one general question. So we had two topics today, so hydrogen, CO2 electrolysis. We're touching upon several aspects related to electrochemical engineering. I love that. We talked about thermodynamics, scale up, lifetime. What can we learn from hydrogen that can we replicate on CO2 electrolysis? That's my general questions for all of you. So do you want to start? Maybe Gareth?
Okay.
Sorry, I was just on mute. Can you repeat that?
Gareth Williams. Gareth Williams, sorry, not Karel.
Okay.
Gareth.
Oh, sorry.
From your point of view, Gareth, I'm curious because you're also active on water, on hydrogen. So what can we learn from hydrogen to speed up scale up for CO2 electrolysis?
Well, for the manufacturing side of things, as I say, as Johnson Matthey is a good example there, we can probably learn quite a lot. So we've got demonstration plants out there and everything. So there'll be learning there, and it comes down to the costs ultimately, the cost of the process and everything. But
I think there are indeed things that you can replicate in terms of scale up manufacturing, but there are also new challenges. For example, selectivity of the catalyst. You get to way more reactions, and now you want to suppress hydrogen evolutions. Can you comment on that? There would be intrinsically different challenges. Yeah,
absolutely. As you say, hydrogen, you only make up pretty much hydrogen, so you get Faraday efficiencies of 99% or something. So the catalyst is key, and the components. I mean, one question I have is, can we make a slate of products, of CO2 reduction products, and then use that as a feedstock downstream? That could be interesting. Rather, I mean, ideally you want to focus on one target product, be it CO, formic acid, or ethylene. You know, very very high selectivities. That's always the best. But I think maybe we may look for opportunities where they can use a sort of a mix of products coming from the electrolyzer and valorize all them.
Yeah.
So I think so.
Thanks. Arend, what is your view if you look at what's happening now in electrolysis and what's happening in hydrogen?
Well, I think, and that was also key in the presentation, what we're running into in the hydrogen implementation of innovations is that it takes a long time to prove your components. There are no benchmarks, there are no standardized testing, there are no ASTs, and that's really an issue that we run into because we want to scale up quite rapidly. CO2 electrolysis being a bit running behind hydrogen, I think should take into account that lesson, that early on you need to think how you're going to benchmark and validate your components for industrial scale, let's say.
Yeah, thanks. And I would like to continue with you, Arend. You can take the first question from the panel. It's like, do you believe we can build 100 gigawatt electrolyzer capacity by 2030 in EU? Or what are the biggest bottlenecks?
It's a matter of are we spending our money wisely if we do that? I mean, technically it's not an issue, but I think actually we already skipped a step when we scale up from 1 2 megawatt systems to 200 megawatt systems. So technically it's possible. Maybe we also need to do that, to stay on course. But in terms of spending the money wisely, I think we should not focus solely on the gigawatt scale, but have an intelligent mix of smaller and larger scale developments where you can learn in a less expensive way, let's say.
Thanks. Does anybody want to react on this question? Anyone else? Not particularly. Well, we're close to the finish, so I actually would like to some final words from your side. Karel first, then Giorgio, and then Matthey.
Okay, so I think from my point of view, main thanks are going to the speakers and to you for presenting this interesting topic on the, let's say, not only from the science and research point of view, but also on the implementation of the technology on the large scale and the obstacles we observe. And I think it's good base for some future seminaries to developing not only this topic, but like another, like the water preparation or water treatment and other issues. So thank you, Michele, for organizing this, and thanks to all speakers and to the participants.
Thank you. Giorgio?
Yeah, just let me say that I'm very happy that this webinar, we had a peak, the one I saw was 211, maybe Martin found a bigger number, but this is what saw a bigger number, but I think this is really quite outstanding. And in spite of the fact that it was rather long, we had a good participation to the end, which is always a good sign. Also, we have a contribution, as you said, from academia, but also from institution and from industry, which is always very important because we have always to see the practical applications of what we are studying. So let me just repeat the thanks to the speaker. Congratulations for the clarity of their presentation and detail of their presentations. I think it was very interesting for me for sure, and I guess for all the attendees. Many thanks. And Martin, you want to say something?
I would like to thank all the participants and of course all the speakers. It was a very nice webinar with a hot topic, and for the participants and for the audience, don't forget to promote this webinar. It will be online. The video will be online on the EFCE YouTube channel very soon. Thank you.
Thank you very much again, Martin, and thank you everybody for joining.
Thank you, Michele, for everything, and Karel as well.
Thank you.
Thank you all.
Ciao.
Take care.
Bye.